Heterogeneous. One reply you got is heterogeneous. Anybody wants to support or talk against? Why heterogeneous? Yeah, it does contain many things, but why do you say it is heterogeneous? Because it contains many things, or it looks not mixed together? It doesn't matter how many things it contains, but the thing is, it does not look in one phase. Milk, it doesn't look one phase because it's very white, liquid, but still you can simply, by keeping it for some time, the phases will be separated. Phase means one state of the matter, like liquid phase, solid phase, and gaseous phase. All right. So this is one phase, another phase. Liquid and solid together, that is we call two phases. But if they are mixes together, that means sodium chloride, that is you put in the water, they mix together and become all solution or liquid, right? Sodium chloride is solid, isn't it? The salt that we eat at home is solid. It's crystal, in fact. So you put in the water, it becomes soluble, solution. It's not solid anymore. It becomes one phase. That's what the phase is. Okay, so now we are going to the the oxidation reduction reaction. And before we move to the oxidation, before we talk about the oxidation reduction reaction, I know that it is very easy for you guys that you already have seen oxidation. What is oxidation? What is reduction? And the very important and convenient mnemonic is oil rig. Who doesn't know oil rig? Who doesn't know oil rig here? From online, who doesn't know oil rig? It's very difficult to check on every time. Yeah, please stop. If you want to ask anything or reply my question, please stop. Okay. So oil rig, oxidation is OIL is losing and reduction is gaining. What is losing and gaining? Of course, it is electron. What else we are talking about, right? Electron. So that element will lose electron. That means it is undergoing oxidation. And that element, it is taking up that electron. That means it is undergoing a reduction reaction. Now, where this electron come from? If there is no oxidation, occurring in the solution or in the process, whether the reduction can occur. Can the reduction occur? If there is no oxidation occurring in the system, can the reduction occur? No, because the reduction, it needs the electron, right? It is taking where the electron is coming from, right? So of course it must make the electron. So that is why we say that oxidation and reduction, it occurs simultaneously at the same time in the solution. So since we understand that oxidation and reduction occurring here, and then oxidation is losing of electron and reduction is gaining of that electron, why would it gain the electron anyway? Why would it gain the electron and why would it lose the electron? Anybody from the online classes, the 6 of you, do you want me to name call you? Huh? Is it easier, right? Sometimes I know that students say, okay, I can answer, but nobody is asking me, If somebody asks, then I will tell. Sometimes students think that way. So should I help you calling your name? Oxidation, what is my question? Yeah. Why some of the elements will lose or take electron? To get the inert gas formation or noble gas formation, right? Or to go nearest to the noble gas formation. That is why they will leave the electron. Another thing is Okay, so this is a very, simple redox reaction, that is magnesium is reacting with oxygen and producing, magnesium is reacting with oxygen and producing magnesium oxide. Magnesium oxide, here it will be one product later on, magnesium oxide will produce. And for this case, this oxidation reaction also need to be balanced, just like other reaction, because this is a double displacement reaction to some extent, right? Or decomposition reaction, or single. It may be, it is this oxidation reaction. So we have to balance this equation. Balancing the oxidation reduction reaction is sometimes daunting, become difficult thing, because of the, you have to keep track of the electrons that moving from here to there, there to here, right? And then balance of the electron. So what we do to make it simple thing is we divide it, and that is called half oxidation reaction. That is means half the reaction is oxidation, half reaction, reduction, half reaction, and both together becomes full reaction. So okay, so now oxidation, why? But another problem is, although we call it that it reaches to that nearest noble gas formation, inert gas formation, so that they will lose or gain the electrons, but that is not the exact thing. There is another problem is some of the transition metals. In fact, the transition metals, here it is. Where is my cursor? Yeah. Transition metals, you'll see that they, all of them has multiple oxidation state, because they can release more than 1, 2, 3, 4, 5, sometimes even 6. What is that? 6 oxidation state. Vanadium, rhenium, it has +6, +7 oxidation state. That means, what does it mean? +6, +7 oxidation state means it can release 6 electrons all together at a time, although it's very difficult for, but it can to some extent. And there are this type of, where is my cursor? Oh, you can see, but I cannot see. So here there are some other outer, except for this transition metal, this is for the non-metals or gases. We see that it is also, no, not argon or krypton, but here we see that is the oxidation state can be changed. Yeah, for krypton and xenon, and then for radon, we do not know about the radon, but krypton and xenon, they also have their oxidation state, many oxidation state, right? And we have seen it during the, we have seen the oxidation state, changes of oxidation state during the Lewis structure. Have you tried Lewis structure? We tried Lewis structure and we saw the oxidation state for the xenon and krypton. It is changing. For helium, neon, argon, it is same. It does not, they are very inert. They do not do anything, participate in the reaction, but the others are, because we know the explanation, they're too big, very hard for the nucleus to keep the electron intact. So electron try to release, and that is why, okay. So so my point here is oxidation number of elements and the compounds, they can be different oxidation number. And it is not only the same for all the time for the element, right? There is a guideline. How do we know that oxidation number rules? What oxidation number for whom? What will be the oxidation number? But it is also, again, it is not the hard and fast, and it is not the concrete thing. It can be changed according to the compound that we will have. At the free element, when we see it on the periodic table, carbon, nitrogen, hydrogen, oxygen, whatever you name it, all are zero oxidation state at the elemental stage. At the elemental stage, it is zero oxidation state. And then in monoatomic ions, the oxidation number as it reflects, like lithium, For lithium, this is monoatomic ion, right? Monoatomic, that means only one atom involved there, and that atom is from lithium, and it is showing plus, so the oxidation state for lithium is +1. For iron, this is +3. For oxygen, -2, so it is -2. And mostly oxygen is -2, most of the time. At least it makes our life a little bit simple. That oxygen is mostly -2, and hydrogen mostly is +1. These two are the, the postulates that makes our life. But this is not always the case. Oxidation is -2 most of the cases, only for, where is it? Okay, only for hydrogen peroxide. Not only, but hydrogen peroxide is the oxidation state for oxygen is -1. Okay, oxidation is -1. And then oxidation state for hydrogen is always +1, except it is attached to the group 1 element, that is sodium, potassium, all those things, lithium. So in this case, it will be -1. Hydrogen is -1, and that is why you can imagine how reactive this compound will be. Hydrogen -1. That means it has to give up one, take up one electron and then become more electron than protons. So in this way, and then yeah, so group 1A metal, that is are +1, and 2A metals are +2, and fluorine is always -2. So this is the only universal thing that we will have here. Number 5. Okay, number 5 is here that group 1 element metals will always have +1. That means lithium, sodium, potassium, rubidium, cesium. They will always have +1 oxidation state. Doesn't matter they are attached to what or where, or they are appearing where. Always +1. And group 2 metals are always +2. That means calcium, magnesium, all of them should always be +2 charge. When they will be charged. Okay, should I clarify this one first? Where they should be charged, and why are we talking about the charges now? Because they are in this charge way, they are attached to one another, forming a compound. A chemical compound they are forming based on their charges, right? So that is why we always write calcium hydroxide. Okay, so calcium hydroxide we write in this way, CaOH. We do not write COOH, or sorry, it is so difficult to write here, or maybe CaCl2 we write, right, always. So that is why, because calcium has 2 positive charge all the time. Magnesium always has the 2 positive charge all the time. So this is the only stable thing that we have, and fluorine will be negative charge always. All right, and 6 says that oxidation numbers for all the atoms in the molecule or ion is equal to the charge of the molecular ions it is carrying. So when we will have sodium chloride, as it is said, sodium chloride, that means there is no charge on it, or HCl, right? We always see HCl, sodium chloride, all those things in HCl or sodium, or okay, give me one name of a compound. Let's say sodium hydroxide, right? Sodium hydroxide. So these are in their natural state. So they are all have 0 charge. All together they are carrying, the total sum of them are carrying 0 charge, 0 charge, 0 charge, 0 charge. But if we break it down, it is what? It is not a 0 anymore. Equal charge and opposite. Like hydrogen will have +1, chlorine will have -1. Is neutralizing and becoming 0 when they are together, and that is why they are together. right? Same goes for positive one, negative one, and becoming 0. So this is the things that I was telling. And here it is saying that the sum of oxidation state for all is 0 unless it is an ion, like bisulfate ion, bicarbonate ion, right? Bisulfate or bicarbonate ion that we have, if we have, okay, so HCO3, we have seen this compound. So what is the charge is not 0, of course. The total charge it is carrying, the whole compound is carrying the -1 charge, right? So this is when they are ions, that is not 0 anymore. It is the total charge that it is shown or they are carrying. Another thing is very not common. It's very few places or few times we should encounter, or probably sometimes we will not encounter, is the superoxide. And superoxide is -half charge, which is even more to the positive side for oxygen, and it is very unstable compound. Okay, so this is the rules of oxidation state, and based on this oxidation state, we should be able to calculate later on where is oxidation and where is reduction occurring. Because to balance the oxidation reduction reaction, first we should identify where the oxidation and where the reduction is occurring. This is very important, right? Okay, so now I'm not going through all this, but you can, and sodium dinitro oxide is decomposing nitrogen and oxygen, and then lithium nitride become lithium nitroid. All these things, and we need to do the oxidation state for the compounds. So one example I will go through only, that for the nitrogen, dinitrogen oxide, right? For this dinitrogen oxide, for oxygen, we it's given here -2, but we already know that oxygen has -2, right? Unless it is superoxide or hydrogen peroxide. Peroxide, then it's different. But if it is not peroxide, then it has a -2, right? So we know that it's -2, and then if it is -2, we don't count the coefficient. For this oxidation state, we don't count the coefficient, right? Only the compound. So if it's -2, but in original state or normal state, it is 0, right? Total charge is 0. So it's -2, and it must be +2 so that it will be total 0 charge altogether. Okay, we understand that nitrogen is +2, but since there are 2 atoms of nitrogen, each will carry 1 positive charge, right? Right. So that is why nitrogen is +1. Okay. So now let's go for lithium nitride. Lithium nitride. So for this, what will be the oxidation state of nitrogen? What is the oxidation state of nitrogen? Let's try to find out by the guideline and then our information. This is what we want to know. So this is positive. No, I didn't want to put positive. I want to say question mark actually. So question mark, this is what we want to know. Well, how do you know that lithium, what will be the, I mean, we have to know one. Only then in respect to that, we will find the charges for the negative, another one. So lithium is group 1 element. Group 1 element is always positive. As I said, number 5 guideline, always positive. So it should be +3, right? Because there are 3, at least 1. So each of them are carrying 1 and 3. So nitrogen should be -3, is it? And then it will be zero charge. So altogether it will be zero. So that is how we should find the charges. What do you call it? Oxidation state. And then after we have found the oxidation state, we will see that, before we go to the balancing of the redox reaction, there is another interesting thing is activity series. I'm sure that many of you have already heard or seen the activity series. So on the activity, those who are the top of the activity series, they are the most reactive, right? So those who are in the top, they are most reactive, and then they will replace those who are beneath them or below them. Like, for example, lithium and potassium, lithium hydroxide, potassium chloride, they are reacting together. Lithium will replace potassium because lithium is much more reactive. And at the end, there is gold. Gold is the least amount or least reactive metal in the world, and that is why it is so stable. And then for 5,000 years, you can find the gold still there. I mean, not decayed or nothing. It's still intact almost because it does not react with anything, almost anything. Aquaresia, yeah, it does react with aquaresia. Okay, so this is the activity series. We should remember how to find the activity series, and then that means the higher the activity series, they are they are very good or very prone to release electrons. They are very prone to release electrons. That means those who are in the top, what is happening? That is, they are oxidizing or reducing. Oil oxidation is losing, so they are getting they are becoming oxidation is happening here. Aluminium active metal, and it is on top of silver, so of course aluminium will replace silver, and then silver will become silver ion. Okay, so balancing the oxidation reduction reaction is simple thing actually. If we just can find out what is where the oxidation and where the reduction is occurring. First of all, we should find out where the oxidation and where the reduction is occurring, and this is important for us too. So for this oxidation reaction, and for the very simple example we have here, that magnesium oxide, let's say it's coming from somewhere, let's say magnesium, sorry, it's not magnesium, it's manganese, right? So let's say it's manganese, potassium manganate, or something like that, okay? So it's coming from potassium manganate or anything, and this iron is iron oxide, or yeah, from maybe iron chloride it is coming from. So this, we are only interested to know the ionic equation, because ionic equation will tell us exactly where to look at, right? Where to look at, where should we find the proper thing, that is the changes are occurring. So for the oxidation reaction, we understand from this equation that iron is going from iron 2 to become iron 3. Can we make it a bigger one? Let's lose it. Okay. Yeah. So for oxidation, iron is losing one electron, and then on the right side is becoming iron 3, right? So that is why iron is oxidized. And then manganese, why do we call manganese become reduction is occurring? Why do we call it reduction occurring? Can anybody explain? If I ask you, if the question asks you that explain why manganese oxide is showing the reduction, why the reduction is occurring here? Why the reduction is occurring for manganese oxide? So for manganese, we see that here it was What is the oxidation state of manganese? I can do it there, right? So everybody can see online and offline. Yeah, good. So manganese was here in this case. Okay, how do you find it? 7, like oxygen is -2, right? So oxygen is -2, so times 0.4 times 4, and then we do not know about the manganese, so just consider it is X amount, and all together it will become -1 ion, because this is the -1 charge here, so -1. So -1. So from, if we equate this equation, it will become X is equal to 7, right? So on this right side, we see that manganese from 7, it goes to 2. So how does it go to 2? How does it become 2 from 7? Yes, yes. Just say. It is taking 5 electrons, right? It is taking up 5 electrons, and that is how it becomes 2. So it's being reduced to manganese 2 from oxide. So that another way you can find out. Oil rig still is the, for me actually it works. I sometimes forget what is the oxidation, what is reduction. So I remember oil rig. But another way you can find out that the oxidation state is reducing. That means the reduction is occurring. Oxidation state increasing. That means oxidation happening. So yeah. So for this case, now we already have find out that where is oxidation and where is reduction is occurring. That means iron is going for oxidation from 2 to 3, and manganese oxide is being reduction happening, so going to manganese ion. Right. So for this case, we need to balance the equation. Where should we add 1, 2, 3, 4 coefficient, and where should we do how do we do that? First of all, in the reactions, okay, you can see, right? I make it bigger, but still, yeah. So in the acidic solution, if the reaction is occurring in the acidic solution, these are the conditions that we should, the information that we should look for before we move for the balance in the equation. Whether the reaction is occurring in the acidic medium, or whether the reaction is occurring in the basic medium, alkaline medium. Sometimes when it is in acidic medium occurring, it is not mentioned. So we assume, we know that it is an acidic medium, right? So acidic medium means what? Acidic medium means there are a lot of hydrogen ions. A lot of hydrogen. We don't have to bother where the hydrogen is coming from. That is. So acidic ion. So this hydrogen ion, which are often used in the balancing of the equation, so that balancing the, first of all, we should try to balance the electrons. All right. Balance the electrons, or balance the the elements or ions that are involved here. So for manganese oxide, manganese is being separated and being reduced. But what is happening with the oxygen ions? The oxygen ion will always produce or convert it to water. In this reaction, oxygen will always convert to water. Okay, so to produce water, I need hydrogen, because there are 4 oxygen atoms. 4 oxygen atom can produce 4 water molecules, right? Because H2O, that means 1 molecule of oxygen, water has 1 molecule, 1 atom of oxygen. So 4 atoms of oxygen will produce 4 molecules of oxygen, but for that case, I need 8 hydrogen. But I do not have to bother because it is coming from the acidic solution. Yeah, it is coming from the acidic solution. This hydrogen is coming from the acidic solution. I don't have to bother. So this is the half reaction. To some extent, we make it balanced in that way. But now, for the oxidation state, that will. Oh, another thing is we do not need to. In this case, oxygen atom, diatomic oxygen, elemental oxygen, or hydrogen, elemental hydrogen, is not involved in this reaction. In this stage, when we are balancing half reaction, in this stage, this hydrogen or diatomic nitrogen or oxygen is not involved. Where what we see that, okay, hydrogen is becoming here we see that it becomes water, right? It becomes the water. This water, this hydrogen coming from this hydrogen, that means acidic hydrogen. It is not coming from this hydrogen. Whatever hydrogen is attached in the solution, this water hydrogen is not coming from there, but it is coming from the acidic hydrogen or protons, right? So since we have found that it is, to some extent, we can balance the equation, the material balance, right? Now we should balance the equation in terms of the electrons, electron number. In terms of the electron number, we should balance. So for iron, we know that it is 2 on this side, left side, which is becoming 3 on the right side, right? It is 2 on the left side becoming 3. That means 1 more electron is being released from the iron molecule, iron atom, in fact, iron ion. So this electron should be shown. This electron should be shown here. Or how many electrons is being shaded or released should be shown here for the oxidation state. And now we are going for the reduction, that is manganese oxide. 8 hydrogen, of course, they have taken it from the acidic medium, but this manganese that we said at the beginning that it is taking a 5 electrons, where this electron is coming from? Hydrogen did not give electron here. It came to take electron from oxygen and becoming water. So the electron was not balanced. So we have to add 5 electrons on the side so that only the right side is balanced electron wise, right? And then you can say that, oh, where do you get this 5 electron? It doesn't matter where I get it. First, I mean, I'm doing the half reaction now. I'm not doing the full reaction yet. I'm just solving the half. So I need 10 electron, 100 electron, doesn't matter. I need it, I will add it. When I make the full reaction, both sides complete, then only I will consider where this electron is coming from. So since this is to the half reaction. So since for the reduction, I need 5 electrons, right? For the reduction, I need 5 electrons. But for oxidation, reduction, as at the beginning also I said that if there is no oxidation, reduction cannot occur because the electrons is coming from the oxidation. So this 5 electrons should come from oxidation. So how do I get the 5? I just multiply by 5. So that means if I have 1 atom of iron, I will have 1 electron. If I have 5 atoms of iron, I have 5 electrons. So that is how I multiply by 5 and then sum it up. Overall reaction is getting this, and then we get the overall reaction. Now this is in the acidic medium, acidic condition. What happens if it is basic medium? What is the major difference in acidic medium and basic medium? What is the in acidic medium there are a lot of hydrogen ion, that means proton. In basic medium we have a hydroxyl ion, right? So now probably you will think that, oh, I add hydrogen to make water. Now how do I make I mean, how can I neutralize the oxygen now? I don't have hydrogen. Yes, that is a good thing. But the trick is, it is very easy to do it. We just need to do the reaction in acidic medium first, same as the acidic, and then where I have added hydrogen, just beside that I add hydroxyl. This is the trick, and it is easy actually. All right. So sometimes if students do not try this at home, then it becomes so hard for them in the exam hall. But if they know somebody listen, then it's so easy, just add hydroxyl beside that and it is done. Just like this. Chlorine and manganate ion that we added. And in the acidic medium, just forget about this. In the acidic medium, I should add hydrogen ion, right, to solve this problem. But since it is basic medium, it says the basic medium, I'm just adding hydroxyl ion. Of course, to the same extent, to the stoichiometric ratio should be same, so that both sides it will be same, or produces water and so on. The rest is hydroxyl ion on the both sides, right? Since I added this 2-hydroxyl ion, I added on the both sides, reactant side and product side. So that means I have solved the problem in acidic medium. That means I had added hydrogen ion, right, on the left side. But now I am telling that it is in the acid, basic medium, alkaline medium. So beside that hydrogen ion, I am adding hydroxyl ion on both sides, reactant side and product side. So these both hydrogen ion, hydroxyl ion are added. And this is how we should be, what do you call it, balance the equation when this is in the basic condition. And don't be scared or don't be afraid of leaving this hydroxyl ion. Oh, sorry. Don't this hydroxyl ion here, because it is supposed to be here because it is in basic medium. So there are we can expect more hydroxyl ion there, right? Just before we saw it was in acidic medium, so we did not bother to throw this hydrogen away because we know that it is in acidic medium, so hydrogen should be there. In basic medium, the hydroxyl ion should be there as well. Okay, hydroxyl ion should be there. Don't be scared or don't bother about that. Galvanic. So now we have some understanding about the oxidation reduction and the balancing of it. We can talk more about the cells, electric cell, galvanic cell. Okay, how the galvanic cell occurs? We have seen in the second lab, I think, second lab, that you put copper in zinc or zinc in copper solution, right? What did you put? Zinc in copper or copper in zinc? You put a strip of copper, zinc in copper solution, copper sulfate, remember? And then you saw the bubble, it came up. So that is, of course, the oxidation reduction was occurring that time, that case. So by the same way, since oxidation reduction means exchange of electrons, and exchange of electron means electricity, right? Sorry, yeah. So exchange of electron means electricity, right? So then, if we have electricity, electron a lot, we can produce electricity. That is the galvanic cell, I mean, the basic concept of galvanic cell. So copper and here spontaneous oxidation reaction produces electric energy. So for this oxidation is occurring, I mean, copper and silver. We have copper and silver, two types of elements are, let's say that, how do you say it? Two types of chemicals we have. Right, we have two types of chemicals. One is metal, that is the copper in metal, and silver, that is in solution. All right, or vice versa, copper in solution and silver in metal form. So when we add together, what is happening is because their difference in the what do you call it, activity series. Just now we have seen the electrical activity series. Now, because of their difference, they will do reaction on both. And since their reaction, copper is losing electrons, so its oxidation is happening, and silver is taking up that electron, so reduction is occurring, right? So this is, by this way we see that the oxidation reduction is occurring. So now if we try to form a galvanic cell based on this information and use these two things to tie up together, so that electron, since the electron is releasing and somebody is taking up, and if we divide these two parts equally so that the electron cannot directly go, it has to travel through an wire, they will give us an electricity. And that is the galvanic cell is happening. So this is the copper, and copper electrode is the cathode, and silver electrode is the sorry, copper is cathode and silver is anode. No, silver is cathode and copper is anode. And why it is cathode and anode, we are saying, where the oxidation is happening, it is the anode, and where the reduction is occurring is, we call this cathode. So for this case, we see that copper is being dissolved in the solution, and then there is a salt bridge for electron to jump from one solution to another solution. And effectively, you can see that there are two cells, there are two half cell actually. There are two half cells. So copper is dissolved in this solution, in the salt, copper salt, and then here silver is being dissolved in this copper salt as well, right? And because of this electron deficiency difference, the electron is jumping from one to another side, and then the electricity is producing. So this is the way that we write the complete cell, zinc and half cell reaction. For here it is zinc and copper. So zinc is in oxidation state is happening to the zinc, and reduction is occurring to the copper. So here we see that zinc, 1 molar of zinc solution, zinc is dissolved, and copper, 1 molar of copper. So this is a half cell. It is representing half cell. This is representing another half cell. We do not go through more detail into this electrochemistry. Probably you will learn electrochemistry somewhere in this when you go through this, your semester. But yeah, this is very interesting cell. And then now there are a lot of different cells, galvanic cell, and then hydrogen fuel cell, and many other things. So you can later we can, if you want to be, you are interested, you can learn more about it. I just want to start and introduce that organic chemistry today, so that we on Monday we'll be able to discuss more about it. I do not intend to go very far or very deep into it. All right. Who is it? Oh my God. It was here. Anyway, so now all right. Okay. Organic. So it was prepared in 2019, but I had added few things in this. So what is this all about for our organic chemistry? We will see the how to do well, and then what is organic chemistry. First of all, what is organic chemistry, the definition of organic chemistry, and then the carbon. Carbon is the basic thing that we start with for the organic chemistry. Again, we will talk about orbitals, bonding and hybridizations, representation of organic molecules, nomenclature, and grouping and classifications. But for grouping and classifications, for grouping, in fact, you should have some hands-on already by this time, because we had done so in the lab. So what is an organic chemistry? What is an organic chemistry? Yeah. Anybody? Any idea what is an organic chemistry? Organic things. There is a very good trend of organic food, organic veggies, organic fruits, all those things. So why do you call it organic? Because for the food and for the veggies, they say that there is no chemical used, right? Chemical fertilizers or anything pesticide used, that is organic. But for us, organic means the materials, the compound that can be found in the living organism. All right, those are organic. Basically, it started in that way. So that is found from the living body, animals, that is organic. But later on, the definition widened. So now we know that what is carbon, hydrogen, oxygen, sulfur, nitrogen is attached in the chain are organic compound. Carbon, hydrogen is the basic block for the organic compound, organic chemicals. Now, this is the organic things, and then what was that? Carbon. Carbon is a very important thing for our building, this organic world. Carbon is the single most important element or atoms that is bonded together all together. All right. If there is no carbon, there is no organic thing. Every organic molecules has carbon. The carbon is itself black, right? We say that carbon is black. Milk has carbon, mostly. A lot of carbon in the milk. So, right? So, yeah, anyway. So now, that is carbon, and carbon is in the 6th group. So it has 6 proton, 6 neutron, and the molecular weight of carbon is what? 12. Yes, carbon is 12, right? So there are 3 allotropes for carbon, that is carbon 12, 13, and carbon 14, right? So this is carbon. More of it we will learn more later on. So description of atomic orbitals. Why do we need to find the orbitals? Because these orbitals are playing a good role in understanding the bonding between the organic compounds or the groups. When we are talking about the organic chemistry, be reminded that we will be talking or we will be learning more about the groups of the organic chemistry. Okay, so these atomic orbitals are important to understand as well. And previously we have seen that 1s2, 2s2, 2p3. This is the electron distribution. But those are from the quantum mechanical perspective, the atomic orbitals are divided in this way. The principal quantum number is the energy level, that is n, that we describe by n, 1, 2, 3, 4. There's the principal. So the more the n, the more the n, fill in the blank. The more the n for an atom, the more is the number of electrons, the size, bigger the size of the atom, right? So the principal quantum number, that is n, angular momentum quantum number, SPDF. So this is how the electrons shape, the orbital shape electrons, how they are staying, or how the cloud of the electrons they are producing. So from their angular momentum of the electron, we can find magnetic quantum number. This is the direction in space, m. Most of the time we will not be very detailed using it, but we know that in a three-dimensional way that S, P, D, F, they all will have their own orientation of the electrons in three-dimensional way, right? So when we are doing on the board, we don't have to bother much because the board is two-dimensional. But when it's three-dimensional, of course, everyone has their own space, own what do you call it, convenience. And spin quantum number, every electron has the spin plus half or minus half. So if rotate in this way is moving, just for example, clockwise plus anti-clock sorry, clockwise, yeah, plus anti-clockwise negative half, and then all the electrons are shaking or spinning in a very fast mode. Okay, so S and P, but for us, S and P will be very important for organic chemistry. And then for Lewis structure, when we started Lewis structure, what was the most important elements for Lewis structure? Only those have p orbitals, until p orbitals, right? Don't forget, yeah, Lewis structure, I mean, you are studying organic, so don't forget inorganic. So from now on, from now today, we will all consider organic chemistry, and we have what we have done so far is all inorganic chemistry, yeah. Now, another thing is on Monday, I will come, we'll bring some those, the shapes, the beads that I showed you one day. So I will give it to you so that to produce your own chemicals. But yeah, later on you have to give it back to me. Okay, so what? Yeah. So this is the how the electrons are going into them. 1s2, then 2s2, then 2p, then 3s in that way. And I'm sure that you already have learned it. Electronic configurations that you have. So shape of the say shape of s and p orbitals, molecular orbitals, then hybridization and bonding shape and all those things we will start. We'll discuss more about next week, Monday. Okay, so thank you very much. It is already 3 p.m. So yeah, I'll see you on Monday morning. This is not the updated one. I have an updated one, which is I cannot find. I didn't copy from my laptop and desktop.